Testing. Okay, good evening. So I hope you enjoyed the typhoon break last week. So tomorrow will be a public holiday. So hopefully you will enjoy the national holiday as well. Okay, so this is where we stopped. Last time we were illustrating this geometric concept on the error mechanism, right? And remember, the error probability is related to the overlapping between the noise cloud. The larger the overlapping area, the larger the error probability would be, okay? So usually the size of the noise cloud is determined by the noise power, so you cannot change it, okay? So what you can change is the geometry of this point, constellation points, because they are noise cloud centers, okay? So, and then we explain, using this geometric concept, we can use that to explain a lot of these comparisons, right? In different, last time I guess I have talked about the BASK, binary amplitude shift keying, BPSK, and then we use the geometric picture to compare and visualize which one can be more efficient, right? And then we explain that BPSK, although you look at the waveform, BPSK 100% is on. BASK 50% is on, right? So you may tend to think that BASK is more power efficient, but in fact it's the contrary. BPSK is more power efficient. And then using the geometric picture, we can even compare how much better, right? So ASK requires 2 units of energy per symbol, but then BPSK only requires 1 unit of energy, okay? So at the end is 2 times better, or 3 dB, okay? We also, I guess, we also talk about the comparison between BPSK and BFSK, right? And then BFSK frequency shift keying, the 2 points are on, so 1 point on each axis. And then we also talk about some weird design, and so that by now you should know how to use the geometric model to visualize the error probability comparison, okay? So this approach would be different from what you have studied in undergraduate because I guess most of the approach that you use in the undergraduate is the algebraic approach. That you go through some probability analysis. At the end, you work out the error probability is a Q function of something, right? So, okay, so what do I want to say? Okay, so another thing is, so this is binary, right? So that's why usually when we specify the modulator, it would be much more convenient if we specify the signal set directly using geometric domain, right? Directly give you the constellation diagram. Because in this case, just using the constellation diagram, you can directly compare the constellation configuration between different designs. So you save the trouble of converting from time domain waveform to geometric points, right? So we talk about binary. So what about 4 points, right? So QPSK, quaternary phase shift keying. The constellation, so the signal set, if I express directly in the signal space, is of this form. It's a 2-dimensional space. This is I, this is Q. And then the 4 points are like this, form a square. Okay? So this is the constellation design for the QPSK. And now looking at this, you see the symmetry here, right? Because now when you have 4 points, you have 4 noise clouds, right? So visualize an imaginary virtual noise cloud overlay on top of each of these points. So you can see the error probability depends on the overlapping area. And the overlapping area now depends on the bottleneck, right? So this, I argue, on a 2-dimensional space, this is the best way to put the 4 points. Because imagine if I have a constellation like this. If I have my constellation like this, then this will not be a good constellation, right? Why not? So you imagine you overlay a noise cloud on top of each point. In this case, what would be the problem? Now remember, each point, the distance of a point from the origin is not free, right? So maintain this distance, you're paying an energy cost, right? So now you have pulled this 2 points away, right? So that means you're spending extra energy on these 2 points, on these 2 symbols. So in order to satisfy the total average energy constraint. That means these 2 points must be put closer, right? Otherwise, you will violate the constraint. The energy constraint is your budget, right? Think about that as money. You spend your money to pull these 2 guys away, right? But your total money is the same. So that means if you spend the money on these 2 guys, the other 2 guys have less money to spend, so they need to move closer, right? So in this way, what's the problem? Then you imagine most of the error will happen between these 2 points, right? In other words, these 2 points becomes a bottleneck. So that's not a good design, right? When you have a bottleneck. So therefore, the money, so-called energy resource, or the distance square, the constraint, should be spent equally among these 4 points, so that you don't create a bottleneck, right? So that's why QPSK constellation will be like this. 4 points on a square, so that you don't have any bottleneck. Is that okay? So, and that's why this is a design that worth a name, okay, QPSK. So now if I have a design that the 4 points are like this, which is just a rotation, okay, what about the performance between these 2 guys? What can you say about the performance? Which one is better? So the difference between these 4 points and these 4 points is the rotation, right? Is there any difference? When I say which one is better, that means under the same bit rate, same bandwidth condition, which one require more energy to maintain the same error probability? Right? Using a geometric model we talked about last time, right? Suppose we set up these 2 constellations in a way that they have the same error probability. That means, geometrically, the distance between these points is, let's call this 1 unit, okay? This is also 1 unit. In this way, the 2 designs will have the same error probability. Is that okay? And then now we compute which one require more energy, right? Obviously, this one and this one is just a rotation, right? With rotation, about the center about 0, the distance of the points from the origin is the same, right? So this design, the energy for design A is the same as energy for design B. Is that okay? Because it's just geometrically a rotation. Rotation doesn't change the distance of the points from the origin, right? Is that okay? So with this simple comparison, we see that both designs will be equally effective. Okay, so sometimes you see QPSK, the signal set specification is like this. Sometimes in some other textbook, you see the QPSK constellation is like this. They are just the same. It's just rotation of the basis by 45 degrees. Is that okay? So rotation will not give you any differences in the performance. How about another design like this? Let's say my 4 points are like this. This is a translation. Okay? So what can you say about these 2 designs? Are they the same? Now this time they're not the same, right? So again, using the same logic, if we want to equalize the error probability, so let's say this length is 1 unit, then that means this length is also 1 unit, right? Okay? And then now we compare which one requires more average simple energy, right? So this one, the average simple energy is this one, right? So you can compute this is 1, 1, then I don't know, using a geometry, you can work out this length, right? And then you can compute the energy. Whereas in this case, the average distance square, right? The average energy will be the distance of this point from the origin, which is this distance square, plus this distance square, plus this distance square, plus this distance square, right? And then take the average. So obviously, this distance would be more than this one, right? It's pure geometry. So therefore, this one will be at least less than this one. This one will burn more energy. Okay? If you want, you can calculate how much more, right? You just compute the geometric average distance square. Okay? So translation will give you different performance. Okay? Rotation of the axis will be equivalent, but translation is a different story. Is that okay? All right, so this is QPSK. Now, the next level, remember when we talk about binary digital modulation, we say that there is one way to increase the bit rate without increasing bandwidth, right? So the bit rate is equal to this term times 1 over TS, right? Bits per second. So, and then my analogy is this term gives you the frequency of minibus leaving the transmitter, okay? This term gives you the number of passengers per minibus, right? So these two together give you the bit rate is number of passengers per second, okay? So, and we explained that this term determines the bandwidth. So for a fixed bandwidth, you cannot change this term. But then you can still have the freedom to increase M, right? The modulation order. You can increase the modulation order to a very large number so that the bit rate can still be increased to a very large number, right? That means in my analogy, it's like you can still squeeze more passengers into a minibus, right? So increase the overall passenger flow. And that seems to be a free lunch, right, at that time. Now let's look at what would be the penalty. Now, so this is M equal to 4, right, quaternary design. You have 4 points on the signal set, okay? Now, if you try to increase M to 8, using the same family of modulation, this is called APSK. You have 8 points. So this APSK means the 8 points are equally spaced on the circle, meaning that each of these points have equal energy, okay? Because they are on the circumference of a circle. Now you compare QPSK with APSK. So what is now this time, let's say we equalize the energy. So let's try to consider this distance is 1, okay? So this is also 4 points on the circle, right? So the circle is unit circle. For this one to burn the same energy, this is also a circle with radius of 1. By this setup, these two designs will have the same average energy. Agree? Okay? So now which one have higher error probability? Of course this one, right? Because for the same unit circle, this design has this distance, right, determining the error probability. Here in this design is this distance determining the error probability. So obviously, if this is D1, and then this is D2, D2 obviously is less than D1. Right? If you want, you can calculate how much less. Okay? It's a geometric problem again. So we know how to calculate how much less, right? We can actually calculate D2 if you like. This is D2. This is 1. This is 1, right? And then this is 45 degrees. No. This is 45 degree. Is it 45 degree? Yes. From this you can calculate D2, right? And then likewise, D1 is this. D1 is also 1 unit here, 1 unit here. 1 unit here, 1 unit here. This is 90 degrees. So D1 will be square root 2, right? And D2 obviously will be much smaller than square root 2. You can calculate this. It's a geometric problem. So therefore, you can see it and quantify how much worse, right? So, but in any case, even if you do not calculate this, you can for sure observe that D2 is much less than D1. So that means when you squeeze an additional 4 points onto the QPSK constellation, you get an 8 points, so you increase the bit rate this way. But at the same time, your error probability will be higher. Is that okay? So that's the penalty. That's the penalty of squeezing more passengers onto the minibus. In this case, there is a higher chance of accidents, put it this way. That's the hidden penalty. And that's why there is no free lunch. Okay? Now, if you want to maintain the same error probability, then what can you do with this APSK? if you want to maintain the same error probability as the QPSK version, the only thing you can do is you need to put the 8 points over a bigger circle, right? This cannot be a unit circle. This must be a bigger circle so that you want to make, let's say this is alpha. In this case, you want to set this guy to be square root 2 so that it has the same error probability, right, as QPSK. And then you figure out what's alpha. So alpha must be bigger than 1, okay? So you can also calculate how much bigger, okay? So that will give you, so that means if you want to go through, if you want to increase the bit rate by doing APSK, by increasing M from 2 to 3, and you want to maintain the same error probability, the price you have to pay is you need to increase the transmission power for APSK. That's why we say there is a trade-off here. When you increase power, you can bring about an increase in bit error rate. You can bring about an increase in bit rate this way. So this direction, in order to engage in this direction trade-off, you need to use some specialized modulation family. For example, MPSK. MPSK is one modulation structure that enables you to do this trade-off. By increasing the power, you can achieve higher bit rate, keeping the error probability unchanged. Is that okay? So this modulation family, so-called MPSK, this is called high spectral efficiency modulation. The way you use that is you want to increase the bit rate without increasing bandwidth. So that's the high spectral efficiency. Spectral efficiency means bit rate normalized with bandwidth. This is called spectral efficiency. So when you engage in this MPSK for large M, you basically increase this log 2M term, increase the number of passengers per minibus. And that is called, number of passengers per minibus is called the spectral efficiency. Okay? So, but the cost of using that is you need to make sure that the signal to noise ratio is sufficiently large in order to support this high modulation order. Okay? Now, so for the MPSK family, so we start with BPSK, the binary version, M equal to 2, QPSK, M equal to 4, APSK, okay, M equal to 8. And then what about if you go to 16 level? Now, of course, you can still continue on this 16 PSK. It's just squeeze 16 points on the circle, right? But then it turns out that if you do 16 M equal to 16, there is a better way to arrange the points on the two-dimensional space. This is the 16 points are arranged this way. And this is called 16 QAM, quadrature amplitude modulation. Okay? Now, I'll explain why this is a better way to put 16 points on a two-dimensional space. But let me explain the name first. So in MPSK, all these points are living in the same circle, right? So why this is called PSK? Because if you change from each point, the 2 points have the same, if you express, now, each point has is on a two-dimensional space, right? So it naturally have 2 coordinates, right? 2 freedom. But the constraint is these M points must be on the circle, right? So 2 freedom, you start with 2 freedom for the coordinate, but then you now have a constraint. So the remaining freedom is only one freedom, right? So if you express the coordinate of each point using polar coordinate, for example, so R theta, right? So that means the differences between these points is only the theta part. The R part is the same. Is that okay? So if you go from this point to this point, the only thing that was changed is the theta coordinate, right? So theta is interpreted as a phase. So that's why it's called phase shift keying, because the differences between the signal points are due to the phase term only. Okay? So you're using the phase difference to signal between different input bits combination. What about this? Why this is called quadrature amplitude modulation? Because if you look at the difference between these different points, the difference between these different points, so between this point and this point, the R theta coordinate, both the R term and the theta term are different. Okay? So that means you are using both the amplitude and the phase term to differentiate these 16 points. Is that okay? So that's why it's called quadrature amplitude modulation. Now with 16 QAM, you have the same formula. The bit rate is also given by this. So bit rate for 16 PSK and 16 QAM are the same. The only difference is which one is more efficient in terms of error probability. Okay? Now I claim that 16 QAM is more effective compared to APSK. That means the error probability of 16 QAM will be less than the error probability of 16 PSK under the same average energy. Why do I claim this? Now, error probability is related to what? The average distance. I mean the bottleneck distance between any two constellation points, right? So if I put the 16 point this way on a square lattice, this is the bottleneck, right? So this bottleneck will determine the error probability. If I squeeze 16 points on a circle, then this distance is the bottleneck, right? So this distance determines the overlapping area between the noise cloud. So this claim is equivalent to saying that if I call this alpha 1, this is alpha 2, under the same average energy. Okay? That means average distance square of this design is the same as average distance square of this design under this constraint. This claim is equivalent to saying that alpha 2 is less than alpha 1. Is that okay? Now, geometrically, why we can have this conclusion? In both cases, it's like putting 16 points on a two-dimensional space. Well, I have a constraint. The constraint is both have to have the same average energy. Average energy, that means the distance square of all these points from the origin has to be the same. Okay? So this is the budget I have. So this way, we'll end up having a larger inter-constellation point distance than this way. Why? Now, of course, you can compute the average distance. You can compute this alpha 1 and compute this alpha 2, and then you know this one is smaller. Okay? But even without tedious computation, you can immediately see this, visualize this. Why? You just think about the exercise, right? Let's say you are asked to put 16 points on a constellation, on a two-dimensional space. Okay? Now, in this way, how many freedom do you have to put the 16 points? Now, each point is living in a two-dimensional space, right? So the coordinate of each point is 2 coordinate, right? So if you look at the polar coordinate, r theta, right? So each point has r and theta being different from each other. So using this design, you have 2 freedom, right? You have 2 freedom to put 16 points on a two-dimensional space under this energy constraint. Is that okay? What about this? If I ask you to put the 16 points using this configuration, how many freedom do you have? Only 1 freedom because r theta, right? But r is the same across all the points. So only freedom you have is theta, okay? So obviously, from an optimization language, you are optimizing the distance, you are optimizing these 16 points on the two-dimensional space under the same constraint, but this one has less freedom, this one has more freedom. The one has more freedom, you will end up having a better design, right? So that's basically the reason you can, without calculation, you can immediately see this is the comparison. Okay? So that means if I draw the error probability versus signal-to-noise ratio, for example, in dB, both design will have this curve. Okay? But this one will be like 16 QAM. This one will be like 16 PSK. Is that okay? That's because in putting the 16 points on a two-dimensional space, using the QAM configuration, you have 2 freedoms to do the job. If you use 16 PSK, you only have 1 freedom to do the job. Okay? The one with less freedom will end up having a poorer performance. Okay? So that would be the comparison. Now, the thing is, the higher the M you go above 16, what about 64, for example? In going for 64, this gap, so you imagine the QAM constellation would be having 64 points arranged on a lattice. 64 PSK will be 64 points arranged on a circle. So you can see that with if you try to squeeze 64 points on a circle, the point and the distance between 2 adjacent points would be very close, right? Would be very dense. Whereas you put 64 points on a square lattice, the distance between the 2 points will be larger, right? So the gap between these two will be even higher. So that's why in practice, you will see people using BPSK, QPSK, APSK. But when you go for 16, not many people will use 16 PSK. Most of the time when you come across 16, they will go with 16 QAM and then 64 QAM. So MPSK is one family, MQAM is another family. These two families is aimed to achieve high spectral efficiency. But then QAM would be more efficient than PSK. Is that okay? So that's why if you look at the practical design like Wi-Fi, 3G, 4G, 5G, if you look at the modulation level in this kind of practical systems, you'll come across BPSK, QPSK, APSK. But then when you go for 16, you don't see 16 PSK. You only see 16 QAM onwards, okay? So when M is larger than 16, when the M is larger than 8, usually people will just give up PSK and then just go for QAM family for this reason, okay? Because the QAM family will be more efficient in terms of the, and will be more efficient, okay? Now, just sidetrack a little bit. There is one exception. There is one exception that you may like to use 16 PSK instead of 16 QAM. This is to consider some practical constraint. Now, in a typical, we see a transmitter data path. You have a baseband, which is doing the memory modulation, right? So these are the transmitter symbol. And then you will have a power amplifier, then to the antenna, okay? Now, so this power, so before the baseband, you have, remember, when we talk about in day one, you need to get a license before you can transmit anything on the air, right? So the license comes with this power mask. This is a center frequency. This is a power mask, right? So you are required by regulation that no matter what you transmit, your spectrum cannot exceed this power mask, right? Otherwise, it's illegal. Okay, so usually in the baseband, you have this what we call pulse shaping filter. The pulse shaping filter will make sure that if you call this ST, this signal you transmit out of the baseband will satisfy this power mask. So if you just look at the spectrum of ST, the spectrum may look like this, okay? However, that doesn't mean your transmitter signal. What matters is this transmitter signal, XT. What matters is the spectrum of this transmitter signal has to satisfy this power mask requirement, okay? Now, from ST to XT, there is a power amplifier. From your undergraduate electronics, I guess with those who study EE, you should have spend some time talking about amplifier design, right? Power amplifier. So what's the problem of this power amplifier, usually? So for low-cost power amplifier, or power efficient amplifier, this guy is usually nonlinear. For example, class C, class D, this kind of power amplifier. They are power efficient, but then they are nonlinear. Nonlinear means if you look at the transfer function, this is output, this is input of the power amplifier. So the transfer function is usually like this. So that means if you're, for example, usually for Wi-Fi or some handheld devices, usually the power amplifier has an average power rating. So usually the average power is 1 watt. 1 watt means 30 dBm. Okay? So that means the average output power, the maximum average output power is 1 watt for this kind of amplifier. So that means within 1 watt average, you are still within this linearity range. You don't have this nonlinear distortion yet, okay? However, the signal input to the power amplifier usually is not a very steady signal. The signal input may be like this. Let's say this is the average power. Okay, the input may be like this. Okay, you know what I'm drawing, right? So this is time axis. The waveform may be varying and suddenly with some peak. So in this case, although you are operating in a linear region on average, right? But when you have this peak may exceed the linear region and enter into the distortion region, right? So the output signal will be like this, but when you have a peak, this peak will have clipping. Okay? So you may have clipping. So the issue is when you have this kind of nonlinear distortion resulting in clipping. If you look at this output signal, so this is the output signal, xt. If you look at the spectrum of this output signal with clipping, the spectrum, sideband spectrum may have a regrowth for this after clipping, okay? So it could happen that if you ignore this clipping issue, your baseband output will satisfy the power mass, but your power amplifier output will violate the power mass, okay? You will have something like this. So this is called spectral regrowth. Okay? Due to clipping. So how do you avoid the clipping? An easy approach is instead of operating at a weighted average power, 1 watt, 30 dBm, you try to back off a little bit, right? You try to back off a little bit to leave some margin so that even when the peak arrives, you don't experience the clipping. Understand what I mean? Right? So let's say this point is the 30 dBm output power level. So instead of operating at 30 dBm, let's say I operate at 20 dBm only. So I leave 10 dB margin for this peak to arrive. And even with, let's say my average power is now 20 dB. And then when the peak arrives, it becomes 30 dB. And even that is still within the linear region, right? So I won't have clipping in this way. This is called power back off. Okay, so how much do you need to back off? Depends on the properties of this signal. This property is called peak to average ratio. Peak to average ratio. So any signal, if you look at the time domain waveform of any signal, you will have some fluctuations. This is time, okay? So those signals with sharp contrast, right? Most of the time you stay with a low level, but sometimes you have an occasional high peak. This is a signal with high peak to average ratio. Okay? Peak to average ratio means the peak power divided by the average power. So it's a property of the waveform. When your waveform has large peak to average ratio, you need higher power back off to avoid clipping. Is that okay? So this clipping or power back off, so this peak to average ratio or the power back off is a penalty. The penalty you need to do to back off your transmitter power so that you avoid the nonlinear clipping, so that you don't have this power spectral regrowth. Is that okay? So it's a cost. It's a cost item. So how much you need to back off depends on the type of signal, or precisely speaking, the so-called peak to average ratio. Okay. Now, after talking about all this, how is it related to us? We're talking about the comparison between QAM and PSK, right? Now, PSK, although by the constellation constraint, is not that efficient compared to QAM, right? Because it only has one freedom. Here you have two freedoms to put 16 points. So this one is more efficient. However, QAM has a disadvantage. Let's look at 16 PSK. If you have 16 PSK, when you change, so as your input bit combination changes, right, from symbol to symbol, sometimes maybe this time, this symbol you transmit this point, next symbol you transmit this point, right? So you're switching between the points over the time duration, right? Since these points, they are on the same circle, right? So when you switch between this symbol, only the phase is changed. The amplitude doesn't change that much, right? So therefore, for 16 PSK, the peak to average ratio for 16 PSK is much less than the peak to average ratio for 16 QAM. On the other hand, if you look at 16 QAM, when you switch between the points due to the input bit combination changes over time duration, if you're from here to here, you will see different amplitude as well. So the amplitude fluctuation will fluctuate more over a larger dynamic range over the 16 QAM. Is that okay? So that's why we have this issue. So that means if you take into account of the power back off in due to nonlinear power amplifier, there may not be an advantage of using 16 QAM because you need to back off by more power. For example, if the peak to average ratio for 16 QAM is let's say 10 dB, whereas 16 PSK is only 2 dB, let's say. That means for peak to average ratio, so that means the power back off for 16 PSK is only 2 dB. So you can transmit 28 dBm at the output of the power amplifier. Just need to back up by 2 dB, right? But for 16 QAM, if the baseband is sending you a 16 QAM signal, although your transmit power, maximum transmit power is 30 dBm, you need to back up by 20 dBm. You need to back up by 10 dB. So your transmit power is only 20 dBm. You understand what I mean? So for the same physical power amplifier, transmitting 16 PSK, you can boost up the higher output power, 28 dBm. But then for 16 QAM, you have to scale down your transmit power. You can only transmit 20 dBm. Okay? So overall, the received signal-to-noise ratio for 16 PSK may be higher than that of 16 QAM because of the different back-off consideration. Is that okay? So it really depends on, so how important this is, really depends on how nonlinear your power amplifier would be, okay? So that would be the practical consideration. Is that okay? That also explains why, for example, I'm not sure if you have ever paid attention to this detail. If you look at the specification of Wi-Fi transmitter, okay? So Wi-Fi, the physical power amplifier for Wi-Fi is 1 watt, which is 30 dBm. Okay? But due to the back-off consideration, so you notice that in Wi-Fi, for example, they have different data rate, different modulation. For BPSK, QPSK, the transmit power is around 26 dBm. That means they need 4 dB back off. Okay? But for 64 QAM, the average power is only around 20 dBm. Okay? So have you ever wondered why from the same physical power amplifier, why you have different power output level? That's because these different signals require different back off. Is that okay? So even we are talking about physically the same power amplifier, maximum transmit power is 30 dBm, but your when your Wi-Fi transmitter is transmitting symbols with different modulation level, the average power that they can transmit is actually different. This is because these different modulation level have different peak to average ratio, so they need different back off. You understand my point? So even though they share the same physical power amplifier, their transmission power will still be different. This is because they have different back off. Is that okay? So this is a sidetrack information for your, so in case, so I don't know, later on when you graduate, you go for a job interview. So depends on what kind of, if you go for a vendor interview, they may, if I were working in vendor, when I'm trying to interview a new student, I would definitely ask him this, okay? So now you know the answer. Okay, now let's back to the big picture. Okay, so this explains this modulation family, either MPSK or MQAM. This is the modulation family you would use if you want to engage in this trade-off direction. So when you use this, you have to sacrifice the power. You want to save bandwidth, okay? You cannot increase bandwidth. So you want to sacrifice the power. You don't mind increasing the power. Power refers to signal-to-noise ratio, okay? You don't mind increasing the power so that you can increase the bit rate without increasing the error probability. So that's the situation when you want to use this modulation family, okay? Now, that's a little bit more elaboration. Now, in practice, as I said, right? So you have MQAM and MPSK modulation family. So you want to increase M so that your spectral efficiency is higher and higher, right? Without paying the bandwidth cost at the expense of extra power. So, but in practice, okay, depends on the system. So, okay, let me explain. So the highest constellation I come across in practical design is like 4096 QAM. So it's crazy, right? It's on a two-dimensional space. You squeeze 4,000 points on a two-dimensional lattice. And this is this exists under this cable TV application. So cable TV is based on a coaxial cable. Okay, so put it this way: in cable TV system, so you may use a different access media, maybe a fiber or whatever. So let's say it's optical fiber, terminate to the building. Okay, and then within the building, you usually use a coaxial cable to do distribution. So this is a cable TV distribution network within the building. They are all based on coaxial cable. Okay, so within a coaxial cable, if you work for a cable TV company, you may need to design how much power amplifier you need to install, and you need to calculate the link budget, whether the signal-to-noise ratio at each household would be good enough to receive the constellation. And in order to maximize the bit rate, right? Because TV broadcasts require huge bit rate, right? So therefore, you want to use a very large M for modulation, and then so this is the modulation system in some of the modern cable TV design. And as I said, right, the condition for you to use this is you need to make sure that the signal-to-noise ratio is sufficiently high, right? Otherwise, the constellation points are too dense together. The error probability will be too high, right? You need extra power to spread out the constellation points on this QAM constellation, right? So that's why you need to make sure signal-to-noise ratio is sufficiently large. So for a cable TV network, this is what we call a noise-limited system. Having a large signal-to-noise ratio is just a matter of your power amplifier dimensioning. You just need to make sure you have a sufficient large power amplifier so that you have a sufficiently large transmit power. Then the signal-to-noise ratio of your distribution network can be controlled to any level you like. Okay? So for this noise-limited system, achieving signal-to-noise ratio to a target level is not a big issue. So therefore, you can usually afford to use very high constellation order. Okay? Like 4096 QAM. However, in 5G, 3G, 4G, 5G cellular network, you seldom come across a modulation of 4096. The highest constellation I come across is something like 64. Okay, for 3G is 64. 4G, I forgot, is something around 64 QAM. Okay, definitely there won't be 4096 QAM in a cellular network. Why not? That never happened. The reason for that is in cellular network, which we'll talk about later on. Cellular network is an interference-limited network. Interference-limited system. That means, for the same reason, if you want to use a 4096 QAM in cellular network, you need to make sure that the signal-to-noise plus interference ratio, in this case, is very large. Okay. However, so that's why I said it's an interference-limited system. The SINR depends on the numerator is the signal power of the good term. Denominator is the noise power plus the interference power. That's called SINR. So even if you increase the transmission power, increasing the transmission power will not bring you an increase in SINR because usually this term scale with the transmission power. The interference also scale with the transmission power. Okay, so when you increase the transmission power, it's just an analogy, right? Suppose in this classroom, I'm the transmitter, you are the receiver. Now in this classroom, which you guys are behaving nicely, if I do not transmit, what do you hear? You only hear the background noise, right? So the background noise power, does that depend on how much power I transmit? No, right? Even if I'm shouting or I'm whispering, the background noise is still the same power, right? So this term doesn't depend on the transmission power, it's a constant, okay? But let's say the class suddenly get kind of very excited and you guys start talking with each other, just like a canteen, okay? In this case, what you still want to hear my voice, let's say. So in this case, if we all talk together with a certain common power, so if we double our power, will you hear a larger SINR? Or put it this way, if you guys start talking with each other, so the total interference power that you experience, would that be related to the transmission power? Of course, right? If each one of you guys double your voice, then the background interference will also increase, right? So this term usually scale with the transmission power. Okay? Now, if I double my voice, of course, the signal term also depends on transmission power. Is that okay? So now you can imagine this ratio determines the quality of the observation, right? So if we all double our voice, if we all increase the transmission power indefinitely, this ratio will be saturated to a certain constant. It will not be increased along with the transmission power. Is that okay? This is the same scenario. You go to a canteen. If everybody is shouting, you won't be able to hear anything. Okay, for the same reason. So cellular network is more like this situation because later on we will talk about this. The frequency transmitted by a base station, by this base station, may be used by some other base station. So it's like a canteen scenario. So every base station is shouting. Okay, so you're a mobile user. What you receive from this base station, what you receive is not only signal from this base station, but also the interference from the other base station as well. Okay, so it's more like a cocktail party in a canteen. So in those setups, it's not like I want to use 4096 QAM. In order to use 4096 QAM, I need to have a sufficiently large SINR. But SINR is not my control. I cannot just determine what kind of SINR you will experience in a cocktail party. I have no control, put it this way. And typically, if you go through a field test measurement in a cellular network, the typical SINR is just around 30 dB, okay, on average. So 30 dB is far from sufficient to support 4096 QAM, okay? So therefore, that's why in cellular network, they never design this into the transmitted modulation, because even if they put in 4096, you never get a chance to use it, okay? So, but the cable TV system is different. In the cable TV distribution network, coaxial cable, there is no interference. So that's why it's called noise limited. And for noise limited system, you can control the SNR at the receiver port to any high value you like by just increasing the transmission power. Whereas in interference limited system, your SINR cannot be controlled to an arbitrary level by just increasing the transmission power. Okay? So that's why it's not just naively increase the modulation order to increase the bit rate. It also depends on the system level. So which we will talk about more at the later part of this part, when we talk about multi-user communications. Okay, just keep in mind there are two types of system. Noise limited system, where you can just control the signal to noise ratio by increasing the power, transmission power. The other type of system is called interference limited system. For interference limited system, you are pretty helpless. Okay, you cannot have too much control onto the SINR received by the receivers. Okay, so you cannot definitely improve the performance by just naively increasing the power, transmission power. Okay, so anyway, so this modulation level will MPSK or MQAM will be the modulation family you can rely on if you want to increase the bit rate without increasing bandwidth. but you need to pay a cost. The cost you have to pay is you need to sacrifice the power, or you need to make sure that the signal-to-noise ratio or signal-to-noise plus interference ratio will be sufficiently large. Okay? The larger the M you go for, the larger the SINR or SNR you need to have. Is that okay? So in a cellular network, which is what we call a wireless access system, usually you cannot have this kind of thing. So this applies to cellular network. This also applies to Wi-Fi. If you look at the design of Wi-Fi, again, you never come across 4096 QAM. Okay? There is one exception, so which I used to work with Huawei on this project. So I helped them to design a 4096 QAM system for cellular network. But that cellular, this 4096 QAM system is not for access. It's not for base station to user. It's for a backhaul that is between base station and base stations. So sometimes they want to set up a wireless link, and this is a wireless backhaul. So they're using higher carrier frequency, like millimeter wave frequencies. And then on this, transmitter and receiver are point-to-point, and they are aligned. Okay? They are not moving. The receiver is not moving, transmitter is not moving. So in this setup, this is more like a noise limiter system. There is no interference in the backhaul. So, so then at that time, I tried to design the 4096 QAM for this wireless backhaul application. And it's not just naively increase the modulation level. So the data path design all have will have a different design compared to conventional one. The reason is because when you need to operate at 4096 QAM, the operating signal-to-noise ratio will be super high. Under such high signal-to-noise ratio, a lot of issues which were not the issue before now becomes a significant issue. For example, phase noise, synchronization error, all these kind of effects. So it will be requiring a different design. Anyway, so just keep in mind, this high-level modulation requires high signal-to-noise ratio. So usually, for extremely large M, you need to make sure that your system is more like noise limiter system than interference limiter system. For interference limiter system, usually the M cannot be too large. Otherwise, you never get a chance to operate. Okay. Now, final explanation for this other trade-off. Okay, what about sacrificing the bandwidth to trade for a lower error probability? Now, this modulation family is also memory. It's MFSK, frequency shift keying. We come across binary FSK last time. Okay, BFSK, the two signals, S1T and S2T, they differ from each other on a different frequency, right? One is on omega 1, one is on omega 2, right? So with MFSK, that means you have M signals in the signal set. Each of these signals different from different frequencies. So S1T has omega 1, S2T has omega 2, etc. Okay, so so what's the difference between this and the MQAM? In MQAM, when we increase the M, the dimension of the space is the same. It's always two-dimensional. Okay, so that's why as you squeeze in more points on the same dimensional space, the points are more congested, right? So you need to use extra energy to separate out the points to maintain the same error probability, right? But MFSK is different. So as we increase M, the dimension of the space also increase. Okay, so M equal to 2, you need a two-dimensional space, but M equal to 4, you need a four-dimensional space. Okay, so then now of course I cannot visualize a four-dimensional space to you. So you just imagine each point is on. So when you have 4 points, but on a much bigger space, the dimension is bigger. So you have more dimension means more space, right? So the space is more spacious. So that when you put the 4 points, you can put the 4 points with the same energy constraint, but the points, interseparation of the points are bigger and bigger because the space is more spacious. Okay? So by increasing M, you increase the dimension of the space, and at the same time, and because of that, the concentration points can be pulled further apart. Okay? Can be separate. The separation between any two concentration points will increase as your space becomes bigger and bigger. Okay, so that's why you can achieve smaller error probability. Okay, but there is no free lunch. The cost you have to pay to support a m-dimensional space. This m-dimensional space is coming from extra bandwidth, because Well, S1t is A cosine omega 1t. S2t is A cosine omega 2t, right? And omega 2 minus omega 1 is 1 over Ts, right? So if you have M signal, M such member, A cosine omega mt, your bandwidth will require M times. Is that okay? So this is the cost you have to pay. You need to pay M times extra bandwidth. But the benefit you get is you get a higher dimensional space, so you have more space to put endpoints. And these endpoints are, for the same energy constraint, these endpoints can be separated over a longer distance. So therefore, the error probability will be smaller. Okay? So if you want to go for this direction of trade-off, you need to use MFSK family. Is that okay? So this family have a name. The previous one, MQAM, is called high spectral efficiency. So this is called high energy efficiency. Why high energy efficiency? Because now if I do not like to reduce the error probability, my error probability is good enough, then by using this MFSK family, I can, since the space is more spacious, right, I can afford to put the concentration points closer to the distance, to the center, right? So I can reduce my transmission power to achieve the same error probability. So that's why this can bring me power saving. Understand the logic? If you do not change the power, using extra bandwidth, using M times the bandwidth, I can get lower error probability because the concentration points under the same distance constraint from the origin, this concentration points will be more separated, right? But if I don't want this extra low error probability, I just want to maintain the same error probability as before, then I sacrifice the bandwidth M times. I can, in a way, reduce the transmission power. Is that okay? I can reduce the transmission power to keep the same error probability. All right? So that's why this is called high energy efficiency. You use this to save energy at the expense of extra bandwidth. All right? So that is the other two trade-off directions. So these trade-offs are not that straightforward. You need to rely on a certain modulation family to trigger this trade-off. Okay. All right. So with this, let me end this topic by giving you a toy example. So remember in day one, I say that there is no universally optimal design, right? So as a competent system engineer, you need to evaluate your situation and tailor-make a transmitter receiver that is most suitable for your situation, right? So now let me give you two situations. The first situation is, let's say you work for a satellite company. Okay? So let's say you want to launch a geostationary satellite. Okay? And your company is selling the satellite. And let's say you work in this satellite company and you're responsible for designing the communication modules in the satellite. Okay? So on the Earth, you have Earth station talking to this satellite, right? So you're talking about this direction of communication, the downlink. Okay, from the satellite to the Earth station. So, based on this understanding, you are the communication module design in the satellite. Which of this modulation family? So you have two choices. Choice one is MQAM or MPSK. Second choice is MFSK. In this scenario, which modulation family would you engage in your communication module? Design one or design two? Let's try to do an opinion poll after all this, right? So anyone pick design one? Design one is good, right? Because it is a highly spectral efficient, right? So with limited bandwidth, you can transmit very high bit rate, right? That's the whole purpose. Design B is you can save power, right? At the expense of extra bandwidth. That's their feature. So this one give you a very large bandwidth, give you very large bit rate, okay? At the expense of extra power. This one gives you very low power at the expense of extra bandwidth. Okay? So which one would you choose in this situation? Anyone will pick design 1? Raise your hand. Okay, 1 or 2, or some sparse hands. Okay, some are struggling. Anyone pick design 2? Okay, good. We have more supporters on this. Okay, so we should pick design 2. Why is that? Let's go through the logic. Well, the framework to consider is we have 2 resource metric, right? One is bandwidth, one is power. These 2 will translate to money eventually, right? So it's the money cost that we want to minimize. Okay? But in this situation, now, if we pick this modulation family, what's the problem? You need extra power, right? Where are the power coming from on the satellite? It's a solar panel, right? So if you need extra power, that means you need bigger solar panel, right? So what's wrong with bigger solar panel? So the satellite, you need to launch a satellite to the orbit, right? To launch a satellite, you need a watt cap, right? You need a watt cap. So the watt cap size depends on the payload. If this payload is very heavy, then you need a bigger engine. With a bigger engine, you have higher cost, higher failure rate, etc., right? So everything will scale up, for that consideration. So for that purpose, you want to try your best to minimize the weight of your satellite. Okay? So therefore, you don't want to pick this, you want to pick this because this design will help you to save power. Save power means saving the area of the solar panel required, right? So in this example, but then by doing this, you need to sacrifice the bandwidth, right? So you need extra bandwidth for that, right? It's not free. So in satellite communication, what is the carrier frequency? It's line of sight, right? The satellite can see the receiver, so it's a line of sight communication. With line of sight communication, you can afford to use a carrier frequency of, let's say, 60 gigahertz. Okay? Because we talk about high carrier frequency, the propagation physics is line of sight. You need to see the transmitter before you can receive the signal. For satellite application, that's fine. That's not too much a problem, right? So at 60 gigahertz, you have plenty of bandwidth. Is that okay? So because of that, in this particular situation, this is less expensive, this is more expensive. So you want to reduce this at the expense of this. Is that okay? Now, of course, I need to hold back on this. I'm talking about this classical example. This is like a geostationary satellite, which is on a high orbit. But these days, you have quite a lot of this kind of low orbit satellite. Low orbit satellite is they are not geostationary. They are moving around, right? So like GPS and in the future 6G, they also have this low orbit satellite as a relay for connecting between the base stations. So for low orbit satellite, this may not be always the case. For low orbit satellite, the launch cost, because you don't need to go to high orbit. For low orbit, you may not need a very big rocket engine to do that, and therefore you may still sometimes you see low orbit satellite using this kind of modulation, because that is not the cost break-even point. Okay. Now, so that's scenario A. What about scenario B? Let's say in the scenario B, now it's on the ground on terrestrial application. So let's say you want to set up a video link between, well, let's say there's some concert in Central, okay, and you want to have a live streaming, set up a video link from Central to UST. Okay, so this is a video link, wireless. Okay, so in this case, you're the designer for this wireless video link. So which modulation will you choose? Of course, in this case, you will pick this one, right? Because this one will give you extra bit rate at the expense of extra power. Now, in this terrestrial setup, power is not that expensive, right? Because you're using utility power, right? But on the other hand, the bandwidth is more expensive in this case because you need, for example, the carrier frequency is much lower in this case. because you want a more favorable propagation physics. So in this case, the frequency may be only 2 gigahertz carrier frequency. So with 2 gigahertz carrier frequency, you may have very limited bandwidth available. So you want to use this family to save the bandwidth, because bandwidth is much more expensive in low carrier frequency, right? You want to save this at the expense of extra power. So that would be the modulation family you choose for scenario B. Is that okay? So this is a toy example to reinforce my statement. There is no universally optimal design. And you need to understand, comprehend the situation. In your situation, which one is more expensive? And then you pick the design to minimize the more expensive resource metric. Okay? Any questions? Okay. So this completed the discussions on the first part. Okay? That is the basic digital modulation theory. Now, so far, we only consider a very simple channel, additive white Gaussian noise channel. So this means the channel just add noise to contaminate whatever you transmit, right? But in practice, we know for mobile communication, for cellular communication, the channel is far more complicated than just additive white Gaussian noise channel. So now, let's look at the next version, the next level of difficulties. Wireless communication over a cellular network, okay? So the first difference is the fading channel. The channel experience something called fading. It's not just a noise, you also have fading. So let me explain the so-called fading. Before we talk about, so we'll talk about several things. First of all, we have to understand, as we said, right? The first thing we need to do is not to design the transmitter or receiver. The first thing we need to do is to understand the channel. So now we're considering cellular communication. So let's spend some time to understand the channel, okay? The mobile cellular channel. Once we understand this, then we'll talk about the impairments, the impact on the performance of the physical layer, on the performance of the digital modulation we just talked about, due to the presence of this mobile fading channel. And then once we understand the impact, then we talk about solution, remedies, okay? So that will be the agenda for the second part. Now to understand the so-called channel, the channel process in the mobile fading scenario, let me just have a thought experiment. Let's say this is a receive power of a mobile. Let's say you carry your mobile phone, okay, and walk around the area, and then you try to record the receive power over time as you walk around, okay? So do you expect your receive power will be a constant straight line as you walk around the area? No, right? It's unlikely, right? So you expect the receive power to fluctuate. Okay? So the first question we want to explore, what is the physics behind this fluctuation? This is due to what causes? What causes the receive power to fluctuate? What do you think? What are the reasons? As you walk along, around the area, let's say you walk around the campus, why you expect the receive power to change? Why not a constant? What is the reason behind? The first reason is due to something called path loss, right? Remember we talked about, so what is path loss? It's the receive power, in general, change with the distance separation. The basic version is the inverse square law, right? If you double the distance separation from the transmitter, the receive power will be reduced by 4 times. That's the basic inverse square law. Remember in day 1 when we talk about the introduction, I have this toy example with a coaxial cable, right? Talking about the long distance communication, right? So at that time we say that the coaxial cable will have 2 effects on the signal you're being transmitted. One is noise, right? Second is what? Attenuation, right? Signal will get weaker and weaker as it propagates down the coaxial cable, right? So what's the physics behind the attenuation at that time? Ohmic loss, right? Because the coaxial cable has resistance, right? So as the signal travels through these resistive elements, you have I square R loss. That's the reason you have attenuation in a coaxial cable, right? Now in a wireless channel, in a radio communication, what is the reason you have this inverse square loss? Why your receive power will be reduced by 4 times if you double the distance separation? that has nothing to do with ohmic loss, right? So if you consider this transmitter, isotropic transmitter, radiating power in all directions, right, in the deep space. So let's consider a receiver point at a distance of d. So let's imagine, draw a virtual sphere center about this transmitter point in the deep space. Okay? By symmetry, because the transmitter source is sending radiating radio wave in all directions, right? If the transmission power at this point is Pt, by symmetry, we can say each of these points on the circumference of this virtual sphere will have the same received power density, right? Because it's isotropic. So by Gauss' law, if you recall from physics, right? Gauss' law, or conservation of energy, the power density that you receive here is given by the total transmission power here divided by the surface area of this virtual sphere, right? So what is the surface area? If this is a distance of d, then what is the surface area? 4 pi d squared, right? That's the surface area, 3D surface area of a virtual sphere, right? So this gives you the received power density at any point on the circumference, right? Agree? So now let's say at the receiver, I put up an antenna. The antenna has a certain aperture, AE, which is the area, effective area. Then the received power is given by AE, this effective area, times this power density, right? Can you see that? So ignoring all the constants, so you immediately see that this is inverse square, inversely proportional to distance square, right? So let me ask you again, what's the physical reason why the received power will get weaker and weaker in the radio propagation in the deep space? You see in the explanation, there is nothing, this is a vacuum, right? So there is no resistance. There's nothing conducting in the vacuum. Still, you have this loss. So why? This is simply because the transmit power or transmit energy per unit time is spread over a bigger and bigger surface area. As simple as that, right? And turns out that the surface area scales like distance square. Is that okay? So in other words, the basic physics behind this inverse square law is the power or energy gets spread over a bigger and bigger surface area, or the transmit power, transmit energy get diluted over a bigger and bigger surface area. Is that okay? There is nothing ohmic loss. So this is different from coaxial cable, right? Coaxial cable, the loss is due to ohmic loss. But here, in radio communication, the basic inverse square law is due to just diluting the transmitted energy. You may argue with me that, okay, here I make an assumption. This is isotropic source, right? Radiating in all directions. What about if I do beamforming? If my transmitter restrict the transmission on a certain angle, okay? So is there anything different from that? Now, let's say the transmitter is only radiating energy with a certain angle, theta. Okay? So, in this case, after some distance, d, we have a certain, this is called sartorial area. Now, we can, of course, use the multidimensional calculus to work out what's the sartorial area, right? Like in terms of the distance, d. Okay? But we don't even need to do that. One thing we can be sure is this surface area was scaled like d squared, right? For sure, this is a fundamental geometry, right? So because of that, using the same analysis, the power density is just transmission power over the surface area. And then your receive power will be given by the antenna aperture times this power density. Okay? Since the surface area must scale in the order of d squared, so obviously, receive power is still given by inverse square law. Is that okay? So it's very difficult to get away from the inverse square law because this is fundamental geometry. Surface area will always scale in the order of d squared. Is that okay? Now, of course, you argue with me that one exception is like if you're using laser. If you have an absolutely parallel laser, then in this case, the surface area in this case, the surface area will be a constant. Then you won't have any path loss. Is that okay? Just like using a laser beam. So laser beam can travel very long distance, right? But of course, in practice, it's very difficult to have a zero solid angle. So even a laser, the transmitted beam is not absolutely parallel. Okay? So for non-zero solid angle, then the surface area must scale like order d squared. And therefore, you will have inverse square law. So it has nothing to do with your isotropic source or whatever. So even if you do beamforming at the transmitter, you still cannot get away from this inverse square dilution of energy. Is that okay? So this is path loss. So now, so what I illustrate is a deep space communication, point to point, okay, the ideal scenario. But in a terrestrial mobile communication, there is usually more than one path from the transmitter to the receiver. When you add up this multipath effect, the path loss formula can be more complicated. So you may have a certain relationship, 1 over d to the power alpha. This alpha is called path loss exponent. Okay, path loss exponent. This alpha depends on how severe is the multipath. It can go from 2 to 4 or even beyond 4. Now, if this is 4, what does that mean? The impact is if I double my distance separation from the transmitter, my receive power will be reduced by 16 times. Okay? So the higher the path loss exponent, the faster the receive power will drop with respect to distance. Is that okay? So this is one reason where we can explain why the receive power of your mobile you expect that to fluctuate as you move around. Because as you move around, your distance separation from the transmitter will change, right? And when your distance separation changes, according to path loss, your receive power also change, right? So that's one reason that explains this fluctuations of receive power. Is that okay? Now, some further discussions on the path loss. First of all, is it a fast or slow process, the time scale of variation? Just using common sense. Do you expect the path loss contribution to the signal variations? Is it going to be a fast variation? Fast means in the order of millisecond. Or is it going to be slow? Slow means in the order of seconds or minutes. What do you expect? What do you expect the path loss will contribute to signal fluctuation on a fast time scale or a slow time scale? So this is due to distance separation, right? We can do some back-of-the-envelope calculation. Now, if you double the distance from the base station, your receive power, let's say, is inverse square. Alpha is 2. If you double the distance separation, your receive power will be reduced by 4 times, right? So 2 times means 3 dB, so 4 times means 6 dB, right? That means you will see a 6 dB difference. Maybe this is a 6 dB difference when you double the distance. So how long it takes you to double the distance from the base station? Cannot be millisecond, right? Unless you can do teleportation, right? Otherwise, if you physically move, your prime average distance from the base station is usually in the order of several hundred meters, right? In order for you to move for several hundred meters, it cannot happen in millisecond, right? So therefore, because of that, you only see 6 dB difference in the order if you can double the distance separation, right? So, and double the distance separation usually takes you minutes, right, or a few seconds, right? So therefore, this is a slow time scale. Slow means in the order of seconds. Is that okay? Now, this is the time scale of variation. Talk about this x-axis, the time axis, right? Do you expect to see very fast fluctuation or very slow fluctuation over the time scale? Now, the y-axis, to describe how much contrast in the y-axis, this is called dynamic range. The dynamic range means the contrast of receive power due to the path loss. So what do you expect? Do you see a large dynamic range or a small dynamic range? Now, for a cellular network scenario, well, so if you are very close to the base station, you basically just next to the base station, you will receive very high power, right? But when you are on the cell edge, then you will receive very low power, right? So later on, we'll have a toy example again to work on the link budget. So the dynamic range depends on the cell size, right? If you have a micro base station, micro cell, usually the cell radius is around kilometer. For a 1 kilometer's radius, the dynamic range can be 140 dB beyond, okay? So the contrast on the y-axis can be huge, 140 dB, okay? So that's the properties of the path loss. Any questions? Now, before I move on, let me ask you one more question. Is path loss your friend or your enemy? Is path loss good or bad? It seems like a silly question to ask, right? It's a loss, right? A loss must be bad, right? But in fact, it is an enemy, but at the same time, it's a friend. Depends on the performance metric. Now, in the context of cellular network, one performance metric is coverage. When you set up a base station, how far can this base station cover, right? So in a region where you have heavy path loss, let's say alpha equal to 4, as I said, right? If you double the distance separation, your receive power will already reduce by 16 times. So in a region, in a market with high path loss component, path loss exponent, the base station with the same power amplifier can only cover much shorter range, right? So with respect to coverage, path loss, of course, is your enemy, right? It's something bad. Because of path loss, you need to use a higher power amplifier to overcome the loss, right? So that is something bad. But I also said that it can be your friend. It's actually a very important friend. Because in addition to coverage, another important performance metric in a cellular network is capacity. Capacity means, for example, how many users you can support in the network. Now, the capacity, path loss is your very important friend, okay? Not only an ordinary friend, but it's very important. Without path loss, there is no cellular network. I can say without path loss, even today, you won't have these affordable mobile phone services, okay? Now, I will leave this to later discussions when we talk about everything else, okay? But just keep this in mind. So path loss, in the capacity sense, is your very important friend, okay? Okay, anyway, so path loss is one reason that can explain this fluctuation of receive power, right? Okay. Now, but is this the only reason? Is this the only reason? Now, I guess we probably should deserve a 15 minutes break. So let's have a break, and then we come back to talk about, is this the only reason that drives the change of receive power? Okay. So let's have a break. This alpha is different from alpha. So my alpha is just up to a constant time for the function. So if you look at the quantum alpha, right, alpha, if the quantum waveform has a short position corresponding downward for extra components of higher frequency. So this alpha is the time for this penalty to this short transition. So my alpha is different from your alpha.
因为它已经是往太空反正就是这边的，我就是那个课开就是开这的话，但那课是比较好不难受，那是真的真难受。你收之前先让我们在多少钱，然后相当于说一会儿看能不能在后面什么第一统一，对，好，经济抱怨。允许能坐一块儿去吃一下，就是看的是够了。下次天天说谁跟谁跳一下，拼接吧。看到。
是你就发达的人会这样。为什么是这样？除以你这张里边有3个点，里边它就是这张每个有3个点。你把那个扣到头上，完全是3个。你意思就是那个人很好。
没有那种反馈的地方。
没有一点空间下降，就是高中的天气很高，出现这种事情小一个点。
把钱箱给砸了。其实一直没事，就他上头一块。
可以了，无水平。 就是他就很糙，他就糙。他有的学校说完成这个事儿，有的学校说很糙，很抽象。我以为你说的是这个，这个是那个，我就懵逼了。对我很重要，对我非常重要。他说你在最后一节课考试，最后一节公路考试，他对我非常重要。他不会在明天考试吧？他如果在明天考试，我就得早提前把我票买走。我包铁全卖给你，但是我说你就是。网上说他有2次。 小红书上面告诉我说，如果你 P 张图片是15的话，然后不是，因为我会做假账，就是。就比如说，我这个简直今天放，你说我今天就准备去发我这件事情放在明天。但是后来我喜欢，因为我发现就是我可能就是看很多好像有些这个片子，你知道做的这些结构对控制是拼。我这个月肯定很辛苦，因为我就是很辛苦，就是能够平衡。
Testing. Okay, so let's resume. Okay, so I was asking the question before the break. So is this the only reason for these fluctuations, right? So in order to confirm this, so usually, so we consider a fault experiment. So the technique we are using is to isolate the dependent factors, right? So since this path loss is due to the change of distance, right, as you move around. So now imagine if this is the base station transmitter, and then now you circle around the base station to move, okay? By circling around, your distance separation from the transmitter is the same, right? So as you move this way, the path loss effect will be neutralized, right? You won't have any path loss variations. So if that's the case, then in this case, do you expect the receive power will be like a constant if you move it this way? If you do not expect a constant, that means beside the path loss, there must be another reason, another process that drives the fluctuations, right? Okay, so of course, by common sense, even if you move this way, circle around the base station, you will still not expecting a constant receive power, right? So then what is the reason that caused the fluctuations? Well, so in practice, if you're here, you may have different blockages, right? So maybe this is a forest, you are blocked by trees, whatever, right? And then when you move to another location like this, you may see buildings, right? This is maybe an urban center, right? So you're blocked by buildings. So when you move to here, you may have line of sight, okay? So when you're in different so-called terrain, so as you move around this way, you will be blocked by different terrain. So this effect is called shadowing. Okay? So shadowing simply means the transmission path between the transmitter and receiver have different blockages. Okay? Blocked by different types of terrain. And different terrain will of course experience different blockages, right? So this shadowing is modeled as this randomness caused by this terrain configuration. So again, let's look at the nature of this shadowing. The dynamic range, the contrast on the y-axis between up and down due to the shadowing process by field test measurement is only around 8 to 10 dB. So it's not quite a high dynamic range process. And the time scale of variation. Again, do you think that this is fast or slow? Fast means millisecond order. Slow means minutes or seconds. In order for you to move to in order for you to move away from the current domain, current terrain, and move to another terrain, it cannot happen in millisecond, right? So usually it will, again, a slow process. Okay, so that's the properties of shadowing. Okay, now the third thing is, we continue to ask the question, right? So now, okay, we identify this may be the second cause that caused the signal fluctuations, right? As you walk around, are they the only cause, right? So using the following similar logic, in order to confirm is there any additional cause, we need to neutralize the two effects, right? So what about now? If we are moving over a certain terrain, okay, like this, do you expect the receive power will now be a constant? Again, probably using your common sense is unlikely, right? So you still expect the fluctuations, right? So that means there must be another process beside 1 and 2, right? That drive the signal fluctuation. So that process is called, let me erase this. That third process is called multipath fading. So multipath fading from its name, meaning that between the transmitter and the receiver, there is usually more than one path. So this is maybe the line of sight path, path 1. This may be the reflected path from a certain scatterer, okay? So, and the aggregate effect is the superposition of these different paths from the transmitter to the receiver, right? Now, what would happen if you have multipath added together? In your high school physics, right? You should, so if you have two sine waves, this is from path 1, this is from path 2. Let's say the two sine waves are phase aligned. That means this peak is aligned with the other peak. When you add them together, what would be the result? You get a bigger sine wave, right? You get a sine wave with a larger amplitude, right? What is this called in your high school physics? This is called constructive superposition, right? Remember this term? Constructive superposition. So the peak is added to the peak so that you get reinforcement of the wave, right? A result with a larger amplitude sinusoidal wave, that means your receive power will be higher, right? So what's the condition for constructive superposition to happen? In terms of phase, the phase difference between the two paths must be integral multiple of 2 pi, right? In terms of path difference, the path difference between these two paths, what would be the condition? Integral multiple of lambda, right? Is that okay? So just very easy. In the phase space, 2 pi is 1 cycle. In the spatial domain, lambda is 1 cycle. So this is more like a currency conversion. In the spatial domain, lambda, this currency, is the same as in the phase domain, 2 pi. So 1 lambda translates to 2 pi. Is that okay? So this is the condition for constructive superposition. Is that okay? Now, what about if you're not that lucky? Let me erase this. What about the two paths? Like this. If they are misaligned, the peak is aligned with the trough. In this case, when you add them up, what's the result? Will you get 0? Not necessary, right? Because the two amplitude may not be the same. But you get mutual cancellation. So at the end, you will have a sine wave with smaller amplitude. Smaller amplitude means weaker power, right? And what's that called? That's called destructive superposition, right? And what's the condition for destructive superposition to happen? In terms of the phase difference has to be what? Odd multiple of pi, right? And what about in terms of the path difference? It's odd multiple of pi translate to half lambda, right? So this will be the condition for destructive superposition, right? Now, if this is kind of new to you, then remember in high school physics, you always have this illustration, right? If you have a source passing through a double slit, right? This is a screen. What do you observe? You observe this dark fringe and bright fringe alternate pattern, right? So this part is the bright fringe, right? Because these two paths have a path difference of 0, right? And then this point would be the dark fringe, right? Because these two paths has a path difference of half lambda, right? And then this spot have a bright fringe again because these two paths now has a path difference of lambda. So on and so forth, right? So you have alternate bright spots and dark spots, right, on the screen. So this is in this physics experiment, it's a one-dimensional pattern of different constructive and destructive superposition, right? So in communication, this is more like a 3D version. So imagine you have a transmitter over there, a Wi-Fi transmitter over there, and let's focus on this ROM, right? So that transmitter, if I'm the receiver, when I'm standing here, I will receive multipath from that transmitter to my location, right? Maybe the line of sight, and then reflection from this wall, reflection from that wall, right? So what I receive, the receive power, will be a superposition of all this together, right? So this dark fringe, bright fringe you imagine in this space, spatially, you will also have a dark fringe and bright fringe, or dark spots and bright spots over the space. So if you turn on that transmitter, you then visualize, imagine that this room will have some spots that receive high power, some spots that receive very low power, right? So high power spots corresponds to the bright spot, where the path difference between this multipath is constructive superposition. The dark spots corresponds to this fading region where destructive superposition happens, right? So the difference is just that the screen is just one-dimensional, but in this space it becomes three-dimensional. So if you happen to stumble into a bright spot, then your receive power will be high. If you stumble into the dark spot, your receive power will be small, right? So that would be the scenario in the terrestrial propagation due to the multipath effect. Different locations will experience different types of superposition. When you are at the spots where you have constructive superposition, then you will receive high power. When you're in the location where you receive destructive superposition, then you will receive low power, right? You may not receive 0 because all these multipaths may not have the same amplitude. But once you have mutual cancellation, the resulting signal will be much weaker. Is that okay? So that is the effect of excuse me. That would be the effect of so-called multipath fading. Okay. Now, this multipath fading, let's also examine the properties in terms of the time scale. Is it a fast time scale or slow time scale process? So that means how long it takes you to move from a bright spot to a dark spot. It's in the order of half lambda, right? So how long is the lambda? So if your carrier frequency is 2 gigahertz, the wavelength is like 15 centimeter. So half wavelength is just like 7.5 centimeters. So how long it takes you to move 7.5 centimeters? Then it will be in the order of millisecond, right? Okay. So this process will be a fast process. Dynamic range. The contrast on the y-axis. The dynamic range depends on the statistics of this multipath effect. So if you do the simulation on a certain scattering environment, and then you collect the differences between bright spots and dark spots, the contrast, statistically it's around 30 to 40 dB. Okay, so it's smaller contrast compared to path loss, but bigger contrast compared to shadowing. Is that okay? So that means when you stumble into the bright spots versus you stumble into the dark spots, the difference in receive power can be up to 30 to 40 dB. Okay? The reason is not that even when you are in a dark spots, your destructive superposition will not give you 0, right? Because you are not only talking about two paths, you talk about multiple paths together. Okay, so it's never cancel to zero. So you still have some power. Okay. Okay, so this is the third effect. So what you observe on the receive power versus time is the superposition of all these three factors. The path loss effect, which is a slow time scale process. So the overall picture would be like this. So these are the three processes. Path loss is basically a slow process. Shadowing is also a slow process. Then microscopic fading or multipath fading is a fast process. Okay, in terms of time scale of variations. So this is one example. So just imagine if you have you do a field test, and then you try to, so this is distance, but this can be translated to time as well. So think about this as time, okay? So if you try to zoom out the time axis, right? So this may be displayed, think about this as time. If the time scale is like minutes, okay? Then these variations like this will be due to path loss, okay? Now if you imagine in this kind of software, you take this piece, small piece, and zoom into this small piece. Then this becomes maybe seconds. Then these variations will be due to shadowing. Okay? Now if you take this small piece and further zoom in, this becomes millisecond. Then you will start to see further fluctuations, okay, within this small time scale or fast time scale. So it's three processes occurring simultaneously but at different time scale. Okay? So this is an example scenario. So as you move, so this is a transmitter. Okay, transmitter signal is coming from this direction. So you imagine the base station is here on this side. Okay, so the mobile is moving along this city center. Okay, so as you move in this direction, due to the path loss, right, your distance separation increases. So therefore, your receive power gradually decreases. This is due to path loss effect. Okay. Now, if you take a small piece and try to zoom it in, okay, you start to see fluctuations. So this fluctuation due to shadowing is in this particular terrain is like this. So this is like Manhattan. So if you're here, due to the multipath effect, so base station is here. So of course you will receive the signal from this direction, but due to the scattering, compressed or complicated multipath environment, another contribution will be from here as well, due to the reflection from the building. Okay. So when you're here, you receive the contribution from these two groups of path. So you are receiving on the low side. Okay. But when you are here, in the crossroad, your receive power will come from this direction, this direction, this direction, and this direction. Okay, so you will receive higher power. So that's why you have the peak. So as you walk across this Manhattan city, you have this alternate pattern because you are crossing the street and the junction, the street and the junction, right? Alternatively. So that's why you have this fluctuation. So this fluctuation is an example of the shadowing. Okay. Now, if you zoom out a certain piece of the shadowing, then you will see these fluctuations. So this fluctuation is due to multipath fading. So even if you're walking on the street, so you will stumble into the bright spot and dark spot alternatively. And this is the separation of bright spot and the dark spot is of the order of lambda, wavelength, or half lambda. So therefore, you will experience this constructive superposition, destructive superposition, alternatively in the order of lambda. Okay, so this is a fast time scale process. Is that okay? So these are the three processes that will contribute to the variations of receive power in a mobile phone, right, as you walk around. Keep this in mind. Now, because of this, let's see, okay, because of this, now it depends on who you work for. You may not, these three processes may have different impact. For example, if you work for operators, let's say China Mobile, after you graduate, so which of these processes will be very relevant to you? If you work for China Mobile and let's say your daily job is to do network design. Network design means you have to determine where to install new base station, what kind of power amplifier to use for a particular base station. Is there any coverage hole in the network? Things like that. If this is your job, then which of these factors will be relevant to you? of course, path loss will be relevant to you, right? Because path loss is a translation of the range and your transmit power. This is called link budget analysis. If you work for operator, you always need to go through this link budget analysis. That is, for a certain power amplifier, you need to figure out what's the coverage of the base station, or the other way around. If I want to provide this coverage, then what kind of power amplifier, how large the power amplifier I need to install at the base station. So these kind of questions will be answered by so-called link budget analysis. So later on, I will give you an example. Okay? In the link budget analysis, of course, you need to consider, because we're talking about range, right? Range is the distance separation. Okay, how far I can separate from the transmitter and I can still receive the signal. That's called a range. So therefore, that requires a path loss model. So you need to understand in your particular environment how the path loss change will be, how the distance affect the receive power, right? So this is called path loss model. You also need to have a shadowing model, right? So in your environment, what kind of shadowing process will be like? Because these two things will affect your link budget. Do you need to worry about microscopic fading? No, rarely, okay? Because microscopic fading is something changing in the millisecond order. So that won't affect your so-called link budget analysis, okay? So usually that's not relevant. Now, on the other hand, let's say if you work for vendors like Huawei or a chipset vendor building a 5G chipset, then which of these processes, and let's say you work on a physical layer design for the chipset, physical layer algorithm, then which of these processes will be relevant to you if you are a physical layer guy? Now, for sure, path loss and shadowing would not be relevant to you because when you are a physical layer guy, you need to determine the algorithm for the so-called physical layer, and that thing will be completed within a frame, right? For 5G, one frame is 1 millisecond. Okay, so that is a time scale you have to work on. Now, within 1 millisecond frame duration, the path loss, the shadowing will be more like a constant. Okay, so it won't affect your physical layer design. Is that okay? So on the other hand, the microscopic fading, since it's changing in the same time scale, the microscopic fading, as we discuss later, will have an impact on the physical layer performance. Okay, so. And because we are talking about physical layer, so we'll focus on microscopic fading. Okay? As I said, we'll try to build model for, this is just a concept, right? So we need to build model to encapsulate the effect of microscopic fading. And based on this model, we then talk about what's the impact, what's the impairment to the physical layer, digital modulation, and demodulation. What's the impairment? Once we understand the impairment, then we talk about typical solutions, the solution roadmap to overcome these impairments, okay? Now, so therefore, again, our starting point is to build model for this microscopic fading. So let's talk about the concept of so-called channel modeling first. All right, so when we talk about channel modeling, let me give you a toy example, right? So for example, if I have a coaxial cable, if the coaxial cable is my physical media, okay, so this is coaxial cable. So if we transmit a signal xt into this coaxial cable, I would get a yt, right? So how do I figure out the yt? So let's say I input a waveform, let's say I don't know, triangular waveform into the coaxial cable. How can you compute the output signal? For those of you who studied EE before, so what would be, how do you do it? If I give you a triangular waveform like this, and ask you to find out what is the output. So how do you do it? There are actually two approaches, right? So in your junior years, I guess you study circuit theory, right? So one way is to refer to the physics. Well, there are two ways to do it, okay? In your junior years, you study circuit theory. So you can build a circuit model for this coaxial cable, right? And the circuit model would be like, so circuit theory. So the circuit model would be like inductor, capacitor, inductor, capacitor. You know what I mean, right? This ladder of inductor capacitor network. If I input xt, a signal here, in this case, do you know how to work out the yt? Using circuit theory. You should be able to do it, right? If you studied EE before. How do you do it? Remember circuit theory gives you KCL and KVL, right? From this, you will be able to form a system of linear equations in terms of the voltage and currents across the network, right? So then with this, you will be able to solve for the output given a certain input, right? So that is not simple and it's pretty tedious, right? Okay. So but that's one way you can use to figure out what's the output for a certain input signal, right? The other possibilities is usually in more senior years, if you study Maxwell equation, EM theory, you heard about transmission line, right? So coaxial cable is a transmission line. So you can start from Maxwell equations and then develop the transmission line equations, and then you can use the EM theory, study the E field and B field, how it propagates in the coaxial cable to figure out the output, right? So this is based on EM theory. Okay, so that's one approach. If I want to figure out the output for a certain given input, you can use circuit theory or transmission line theory to figure out the output. But this approach requires heavy domain knowledge, right? You need to understand EM theory, or you need to understand the circuit theory in order for you to be able to do the job, right? So in your senior years, you study something else, right? So-called system theory. So system theory is like a black box approach. So you consider this coaxial cable as a black box. This black box has an input, it has an output, right? And then usually the system theory you study is called linear and time invariant system. So if you have a linear and time invariant system, then what is the parameter that defines the behavior of this black box? It's called the impulse response, right? Remember. What is the impulse response? The definition is if your input is an impulse, then the output would be the impulse response. Is that okay? Now, if you know about the impulse response, then how do you figure out the output? The output is given by the input convolution with the impulse response, right? That's what you learn in system theory, I guess. Okay? So it seems like when I figure out the output for a general input, I don't need to know the physics, right? I don't need to have any domain knowledge. As long as I know the impulse response, then I would be able to mechanically compute the output for any given input by doing this convolution. This convolution doesn't require domain knowledge. You understand the difference? So this is a huge difference compared to this traditional approach. This traditional approach is you open the box, you look at the circuit, and you go through this case-by-case analysis. But this system theory approach is you encapsulate all this detail with a black box, right? Once you know the parameter of this black box, then you can compute the output for any given input without knowing physics, right? So if I tell you there is an LTI system, I give you the impulse response. Even if you have never studied physics before, you can still work out the output. Is that okay? So where is the domain knowledge hidden? The domain knowledge, the physics, is actually encapsulated into this impulse response, right? So how do you find out the response when your input is a delta function? You still need to rely on the physics, right? But you just need to do it one time. You just need to solve this equation for delta t as your input. You just need to do it one time. Once you figure out the impulse as the output, then all the physics is completely encapsulated by the impulse response. You can throw away the physics, right, for the future evaluation of the output. Is that okay? So that's the black box approach. Now, of course, you don't need to work it out analytically. You can even do experiment, right? You can inject an impulse and look at what is the output. That is also another way to measure the impulse response, right? So, but conceptually, even if you have to derive it theoretically, the physics domain knowledge is now completely encapsulated by this impulse response. Once you know the impulse response, the physics will be irrelevant. Is that okay? So this is why so-called channel modeling is we want to take this black box approach. Okay? So in this example, the coaxial cable, the so-called channel model is encapsulated by this channel response or the impulse response. Is that okay? So if you buy different coaxial cable, so if this is a series cellular, each coaxial cable will have their own impulse response. Okay? So you just need to, when you buy a coaxial cable, you just need to ask for the impulse response. And that's all you need to know, because that completely encapsulates the physics for the coaxial cable. Is that okay? So now, but of course, when we do this black box, we need to make sure that this is an LTI system, right? Otherwise, if this is not LTI system, then this theory doesn't work, right? So how do you know this is? Now, LTI is two properties, linear and time invariant. What is linear? If I give you this coaxial cable as a black box, right, or I give you a black box with input and output, how do you know whether this is linear or not? What do we mean by linear? Any idea? I'm sure you heard about linear system all the time. But what do we mean by linear? So linearity is equivalent to a concept called superposition. Okay, so what do we mean? If I have a black box, if my input x1t, my output is y1t. If I input x2t, the output is y2t. Okay, and now if I input alpha 1 x1t plus alpha 2 x2t into the system, I ask what's the output. Okay, if the output is alpha 1 y1t plus alpha 2 y2t, if this is the case for all alpha 1, alpha 2, for all x1, x2, then this is called superposition principle. And this is called a linear system. Is that okay? So linearity, always think about superposition holds. Okay? So superposition means if you input a weighted combination of the signals, the output will also be the corresponding weighted combinations of the outputs. Okay? Now, with this understanding, is this coaxial cable linear? We cannot just close our eyes and apply LTI, right? We need to see this is the model for this physical cable. We need to check whether this is a LTI system, right? So linearity first. Is this linear? Of course, you will guess this is linear, right? But why this is linear? Well, you can have two ways to look at that. One way is using circuit theory, right? So this circuit model is like this, right? So if you look at this circuit element, all these elements are linear elements, right? So the circuit response must be linear, right? The other way is look at transmission line. If you look at transmission line, the transmission line is coming from Maxwell equations, right? So at least you heard about Maxwell equations, right? If you look at the Maxwell equations, it's the four partial differential equations. These Maxwell equations are linear operators, right? So the fundamental laws of physics is linear. So therefore, the result of these fundamental laws would also be linear, right? So from this other angle, from the physics angle, you also can be sure that this coaxial cable will be linear, right? The cable itself. Okay? So it's linear. That's good. What about time invariant? What do we mean by time invariant? What do we mean by time invariant? Conceptually. That means I have a box. I give you a box, right? You try to measure the properties of this box at t equal to 0. You get some result. If you measure it 1 minute later or 2 minutes later, you will still expect the properties will be the same, right? That's called time invariant conceptually. Mathematically, how do we express this? So if I inject an input at time t, right, I get a certain output. Now if I inject the same input but with a delay time, okay, at tau into the system, then I ask what will be the output. If the output is yt minus tau as well for all tau, then this is time invariant mathematically. Is that okay? So is this time invariant, the coaxial cable? Yeah, of course, you will guess it must be time invariant, right? But why? Why it is time invariant? How do you know? Again, you look at this circuit model, right? If you look at the circuit model, all these L and C, they are basically time invariant elements, right? The capacitance and inductance are not changing with time, right? So therefore, the circuit behavior would be time invariant. That's one way to look at that, right? Is that okay? The other way is to look at the transmission line equations. Again, the PDE is time invariant. The coefficients of the PDE are constants, independent of time, okay? So this gives you the confidence that this is also time invariant. So you need to check this before you can safely use this LTI model to do a black box modeling of your coaxial cable. Is that okay? So why I mention this? Because we are not talking about coaxial cable. We are talking about the multi-path fading channel, right? But we also want to use the same black box approach to do the channel modeling. So let me draw our scenario. Okay, so let's say. So in this case, we have a transmitter. We have a receiver. And then we have multi-path. Okay, so this is a chaotic situation in the radio propagation, okay, affected by multi-path. So if I input a certain xt, same question to the transmitter, I want to figure out what's the output, right? So if I use the domain knowledge, the physics, right? So how can I work out the outputs? Well, I need to start from Maxwell equations, right? Or I can do ray tracing, right? So I can model each individual way, and when you come across an obstacle, I can model the reflection. So if I have a 1,000 path added together, then I physically generate 1,000 path and add this 1,000 path together, right? So basically start from EM theory. So this is, again, requiring strong domain knowledge, right? And even if you can solve it for a triangular wave, next time if I ask you to find out what is the output for a rectangular wave, you need to do this all over again, right? So it's not very helpful. And with this, it's difficult for you to get an insight, intuition on the overall effect of this channel, right? It's the same idea. So we would like to take a similar approach, a system approach. So that means we want to model this thing as a black box. So we have a black box with a certain input and certain output. Okay, we want to do the same as how we model the coaxial cable. But now, the first thing we need to check is whether this is LTI system, right? Whether this is L and TI. So first of all, is it linear? Now, to judge whether this is linear, you need to go to the physics, right? So what would be your judgment? Is it linear in this propagation channel? It's linear, right? Because the foundation of this Maxwell equation are Maxwell equations. As I mentioned, the Maxwell equations, the operator, the differential operators in the Maxwell equations, they are linear operators mathematically. So therefore, the propagation itself is linear. It's a linear process. Okay, so this is linear. Is it time invariant? Is it time invariant? Now think about this situation. This is a mobile communication system, right? Transmitter is the base station, which is fixed, right, not moving. But the receiver is moving, right? You are moving all over the place. So remember what is the intuition behind time invariance? Is I give you a black box. Let's say you take this coaxial cable. You measure its property at t equal to 0. You got one result. If you measure the property 10 minutes later, you will still expect the same result, right? That is called time invariance. Now, in the case of this mobile communication, if you measure the properties at t equal to 0, the mobile may be in this room. If you measure the properties 10 minutes later, the mobile may be outside this room, right? So the environment can be different. So therefore, it is not time invariant. Well, what if you say that, okay, let's say I'm a mobile user, I'm standing here, I'm not moving. Now the transmitter is not moving, the receiver is not moving. In this case, will this be time invariant? If both the transmitter and receiver are not moving. So is this a time invariant system? Still no. Why not? The channel will change. What do we mean? So the physical. So let's discuss in terms of the physics. Why? What do we mean by the channel will change? Why? What drives the change? What drives the change? Yes, it will still be time varying. But what drives the change? If the mobile is not moving. Even the mobile is not moving, the scattering objects may be moving, right? So maybe this is a lorry passing by. Or if this is a person just walking by your coverage area, right? So he may just leave this room, right? So before he leaves this room, he may be a scatterer. After he left this room, he will not be a scatterer. You know, the environment, the scattering environment, scattering objects will also be moving, okay? So it's very difficult to make sure everything is static, okay? So therefore, this is not time invariant. It's called time varying. So what we have is a linear and time varying system. So therefore, the question is, now, okay, how do we deal with linear and time varying system? How do we model? So what would be the parameter that can completely specify the behavior of this linear and time varying system? Okay, fortunately, it's still linear. So we can extend from this LTI system into something called linear time varying system. Now, for those of you who study EM theory, Maxwell equation, you should learn about a concept called Green's function, right? So Green's function is just an example of this LT, linear and time varying system, okay? But if you haven't heard about Green's function, whatever, it doesn't matter. So in a linear time varying system, the corresponding parameter that completely encapsulate the behavior of this black box is still an impulse response, but this impulse response becomes two-dimensional. It's time varying and depends on the delay. So the impulse response is now generalized to a two-dimensional function, put it this way, okay? This time encapsulates the mobility, the time variation. The time variation, of course, as I mentioned, is driven by mobility of the physical objects, either the mobile receiver or the environment or the scatterer, okay? This second dimension is to model the so-called multipath. Okay, so how many paths arrive from the transmitter to the receiver? What will be the delay, response, etc. So this is the multipath dimension. So you need to, if you want to fully characterize this LTV system, you need to construct or you need to know this two-dimensional impulse response. Okay. Now, of course, knowing the two-dimensional impulse response would be more tedious compared to this case, where you have the impulse response is just a one-dimensional function. Okay. So you need to capture the time variation component as well. Is that okay? But conceptually, it's the same. Okay. It's just a more complicated parameters to define the behavior of this black box. All this physics, all this multipath propagation will be completely encapsulated into this two-dimensional impulse response. Once you know about this, you can forget about the physics and just treat the connection between the transmitter and receiver as this black box and forget about the physics involved. Is that okay? So that's the beauty of so-called channel modeling. Okay. Now, of course, if I want to have a precise specification of this multipath channel, I need to work out this impulse response, right? But we'll take an easier approach. So it's like, I don't want to have a precise description, but I want to define some parameters. So this is the two-dimensional impulse response. Once again, this is to encapsulate the time variation. This is to encapsulate the multipath. So instead of talking about the precise function of this two-dimensional impulse response, we want to define some parameters, some numbers in this two dimension, in this two domain. Okay, we need to define some parameters. So knowing these parameters, of course, will not give me a precise description of the two-dimensional impulse response, but it will give me some idea what would be the two-dimensional impulse response look like. This is the same as in a coaxial cable case. In a coaxial cable, I have an impulse response, right? One dimension. So instead of looking at the full description of this impulse response, which is much easier, but still costs some effort. Sometimes you go to buy a coaxial cable, you may not be able to get this full impulse response. Instead, they may give you some parameters. For example, the parameters may be bandwidth. It's a number, right? Maybe this coaxial cable has a first order bandwidth of 800 megahertz. So of course, knowing 800 megahertz doesn't give you the specification of this impulse response, right? But it gives you some idea how this impulse response look like, okay? So we are going to take a similar approach. So instead of talking about the full description of this multipath fading channel, we are going to talk about introduce some parameters for each of these dimensions, so that these parameters cannot fully describe this, of course. But knowing these parameters, these numbers, first of all, they are easier to obtain and easier to be measured. And second of all, knowing these parameters will give you some ideas, some intuitive ideas about how this impulse response look like. Okay, so I don't think I have time to cover this other part. So let me stop at this point, and then I will talk about these individual parameters in each dimension next time. Okay, so I leave earlier so that you can have more time for the holiday break. Okay, so let me stop at this point, and see you next Tuesday.